Let's try section 5.3. Maybe that one's easier. Section 5.3, we're going to talk about matrices. So those of you who are in linear algebra should find this very, very easy. What do you know about matrices?
Not a lot.
That little box there.
The little box thing. And usually they have numbers in them. All right, so this spot is usually called spot A11. And what do I mean by A11?
First row, first column.
It's first row, first column. So what would I call that spot?
A12.
A12.
A1.
First row, second column. And then this would have A13, and maybe this one has A14 going across. So this one has 4 columns. And then how about if I go down to the next row? A21, A22, A23, A24, so on and so forth. And A31, A32, A33, and A34. Okay. Usually these things are numbers, but they don't have to be numbers. They could be functions. And we will talk about matrices that have functions in them here in a few minutes. All right, the first thing we need to know about matrices is how do you add, subtract, and multiply matrices. So if I gave you the matrix, if I gave you the matrix 1, 2, 3, 5, negative 2, 4, and I asked you to multiply it by 3, what would you do? You multiply each number by 3. So that would be 3, 6, 9, 15, negative 6, and 12. That's called scalar multiplication, which just means you're multiplying by a number. What if I gave you the matrix 4, 2, negative 3, 5, and I asked you to add that to the matrix negative 2, 3, 8, negative 1? How do you add matrices?
Add the A11 with the other A11.
You add component-wise. So to add, you're going to take 4 plus negative 2. That's 2. 2 plus 3. 5. Negative 3 plus 8. 5. And 5 plus negative 1. 4. Okay. What if I asked you to take the matrix 1, 2, 3, 5, negative 2, 4, negative 4, and 2, and add it to the matrix 3, 0, negative 1, 8? What would you tell me the answer is?
Undefined.
Undefined. Why not? The dimensions do not match. What do you mean the dimensions do not match?
2 by 3. 3 by 2.
This one is 3 by 2, which means 3 rows, 2 columns. And this one is 2 by 2, 2 rows, 2 columns. In order to add, what has to happen? The matrices have to be the same size. This one's 3 by 2, that one's 2 by 2. They're not the same size. We can't add them. So we just say it's undefined. Questions on that? Okay. How about multiplying matrices? Same 2 matrices. 1, 2, 3, 5, negative 4, 2. And I want to multiply it by 3, 0, negative 1, 8. You can multiply those, even though they're not the same size?
Yep.
All right, so how does multiplying work?
You have to have the same.
Okay, so this one is 3 by 2, 3 down, 2 across. This one's 2 down, 2 across. In order to multiply, those two numbers have to match. And then how does that multiply thing work?
Row by column.
You multiply row by column. So you go across this row and down the column. So you take 1 times 3, 2 times -1, and you add them together, and that goes in the upper left-hand corner. So you take the upper row, the left column, you multiply, and add, and that's what goes in the upper left spot. What's going to go in the upper right-hand spot?
Row, second column.
You're going to use the first row here, second column there. So you're going to have 1 times 0 plus 2 times 8, which is 16. Correct. All right, so your final answer is looking like this. You have 3 plus -2, that's a 1. And there you have a 16. Now what? Repeat the process, except now go down to the next row. So the next one you're going to have 3 times 3, 5 times -1. That's 9 plus -5, that's 4. And you keep going. 3 times 0 plus 5 times 8. 40. And then finally, down to the last one. So you're going to go across and down. -4 times 3 plus 2 times -1. -14. And the last one would be -4 times 0 plus 2 times 8, 16. So there would be your answer when you multiply those two matrices. Questions on that? Okay, so again, in order to multiply, these two numbers have to match, and then the answer that you get will have the size of these two outside numbers. So that one's 3 down and 2 across. It's always the outside numbers. Why do we multiply in that weird way? What works? I mean, it would. That seems awful complicated. I mean, if I had 3, -2, 1, 5, and I wanted to multiply by -1, 4, 8, 2, doesn't it seem to make a lot more sense to take 3 times -1, put that in the upper left corner, -2 times 4, put that in the upper right corner, so on and so forth?
Isn't it like a, you almost have to do scalar multiples of every element in the other matrix?
Yeah, that's exactly what you're doing, but why?
Don't you have 2 series of equations for each one of those matrices and you have to multiply those? Like, wouldn't it really be like 3x minus 2y times minus 1 another variable?
Yeah, that's really what we're going to end up with. It'll make more sense why we multiply this way in a minute when we talk about writing equations in terms of matrices. All right, so what would the answer be? Three times -1, -2 times 8, -19. 12 minus 4, 8. Then I'm going to have -1 plus 40, 39. And finally, 4 and 10, 14. All right, well, what we're going to use matrices for in this class is we're going to rewrite systems of equations using matrices. So for example, I might give you, steal one out of the book here. X prime equals 3x minus 2y. And y prime equals 2x plus y. What we have is we end up having a system of equations. We have two equations with two variables. What we're going to do is we're going to rewrite that as a single matrix equation. So we're going to write this way. X prime, y prime as a matrix equals 3, negative 2, 2, 1, and then xy. That's a 3. So now this multiplication makes sense. If I go across and down, what do I get? 3x minus 2y. And then this one I go across and down, I get 2x plus y. All right, now more specifically, this is usually written as the vector x prime equals 3, negative 2, 2, 1 times the vector x. In the book, instead of writing a little arrow on top of the x's, they tend to put their vectors in bold font. It's hard for me to do bold font on a piece of paper, so I use this symbol to represent these are really matrices. So in essence, what have we done? Hopefully made the problem easier. Well, it kind of looks easier. We started with two equations with two variables. And in a sense, what we've done is we've reduced it to be one equation with how many variables? Just one, this vector x. So what we'll talk about in the next section is how do you solve this sort of matrix equation. Questions on that? All right, the next kind of homework you're going to see, you're going to be given something like this. X prime equals negative 3, 2, negative 3, 4 times x. And they give you x1 equals e to the 3t, 3e to the 3t. x2 equals 2e to the negative t, e to the negative 2e to the negative 2t. No initial conditions. E to the negative 2t. So what they're doing, this is problem 22. They're giving you a differential matrix equation, and then they're claiming that x1 is a solution and x2 is a solution. And you need to prove that x1 is a solution and x2 is a solution. How would you prove that x1 is a solution to this equation? Substitute it in. So you're going to take x1, you're going to take the derivative, you're going to plug in the derivative, and then you're going to take x and you're going to plug it in there, and you're going to do the matrix multiplication. And then what should happen?
Equality.
You better get the same answer. It's going to happen. All right, so let's try it. Using x1, I get, when I take the derivative, what's the derivative of e to the 3t? 3e to the 3t. 3e to the 3t. 9e to the 3t. So to take the derivative of a matrix, you simply take the derivative of each coordinate. Equals negative 3, 2, negative 3, 4, times our matrix X, which is e to the 3t, 3e to the 3t. Do the matrix multiplication. What do you get when you take negative 3, 2 and multiply it by e to the 3t, 3e to the 3t, 3e to the 3t? You get negative 3 plus 6. Negative 3 plus 6 is 3. E to the 3t. That's good because that one matched. That one times that one. Negative 3 plus 12. Negative 3 plus 12 is 9. So is x1 a solution? Yes, it is. Do the exact same thing with x2. For x2, I'm going to have negative 4 e to the negative 2t and negative 2 e to the negative 2t equals negative 3, 2, negative 3, 4 times 2 e to the negative 2t, e to the negative 2t. I work out the multiplication. Negative 6 plus 2, that's negative 4, e to the negative 2t. And then I have negative 6 plus 4, that's negative 2, e to the negative 2t. Questions on that? When's the other shoe drop? Well, the big question is, if I gave you this equation, how did they come up with those two solutions? So at this point, they're just giving them to you and saying, plug them in, make sure they really work. The question is, where did they get them? And we'll talk about that soon. But let me ask you a bigger question. For this system, we came up with two vector solutions. How many solutions should we come up with? Infinitely many? Okay, so where are all the other ones? They are scalar multiples. What we really had here, this x prime is really this equation, remember, could really be written this way as x prime equals minus 3x plus 2y, and y prime equals minus 3x plus 4y. That's what that original equation written as a system really was. And so what did we just find here? Our answers are x equals, x has to have an e to the 3t and a e to the negative 2t. So our answer is x equals c1 e to the 3t plus 2c2 e to the negative 2t. And then what would y be? No. Y would have a e to the 3t and an e to the negative 2t also. It would have a 3c1 e to the 3t plus c2 e to the negative 2t. So this is going to be the general idea. We're going to start with a matrix equation. We're going to find, if we start with a 2 by 2 system here, we're going to find two vector solutions. What happens once you find two vector solutions?
Write them as equations.
You can write them as the equations, and you found all of these solutions. Y has a 3c1 e to the 3t plus a c2 e to the negative t. But we need to be careful. When we find our two vector solutions, what do we need them to be? We need them independent. And how do you determine if they are linearly independent? You use a Wronskian. So we need to talk about what's a Wronskian for two vectors. But this is the general idea. The general idea is it's the exact same thing we did in Chapter 2, except in Chapter 2 we had second-order differential equations. We had to find, if we had a second-order equation, we had to find two solutions. We needed them to be linearly independent. Once we knew they were linearly independent, we had a big theorem that said once you have two linearly independent solutions, you have them all. And so that's really what we need here. We need the equivalent theorems here. If you have a 2 by 2 system, you need to come up with two linearly independent vector solutions. Once you have two linearly independent vector solutions, you have all solutions to the differential equations. All right, so that's where we'll start on Wednesday. We'll start with a list of theorems that says all that stuff works.